Every single time your spark plug fires, not every drop of the fuel you paid for is converted into motion. Some of it never contributes to pushing the pistons or moving the car forward in the way drivers imagine. Instead, part of that fuel can remain incompletely burned and leave the engine as wasted hydrocarbons, which is why the idea of burning money feels so real to so many drivers frustrated by rising fuel costs. That frustration has helped create a massive fuel additive market, an industry worth billions of dollars each year, built on the promise that one bottle can restore power, improve mileage, and fix hidden inefficiencies inside your engine. Walk into almost any auto store or gas station, and you will see those products placed where impulse buys happen most easily. Bright labels, bold claims, and price tags that often stretch from around $12 to more than $20 for a single treatment. The business model is simple. Sell drivers the feeling that they are finally correcting a hidden problem under the hood, while the real manufacturing cost of many treatments is only a fraction of the retail price. That enormous gap between low chemical cost and high shelf price is where the illusion becomes profitable. And it is exactly why so many consumers never stop to ask what is actually inside the bottle, what the evidence really says, and whether the claims are as revolutionary as the packaging suggests. At the center of this controversy is acetone, a common industrial solvent with the chemical formula C3H6O. For decades, it has appeared in debates, garage experiments, and fuel economy folklore as a supposed performance booster, with supporters claiming it changes how gasoline atomizes and burns under pressure. Critics, however, warn that such claims are often overstated, inconsistently tested, or presented without proper real-world verification, especially when modern engines, fuel systems, seals, and emissions equipment are designed around very specific fuel standards. That is where this story becomes bigger than one chemical. It becomes a story about how billion-dollar industries, desperate consumers, half-remembered technical claims, and the promise of a cheap miracle fix collide in a market where hope is easy to sell and hard evidence is much harder to find. Long before modern internet forums and viral automotive channels began recycling the same miracle fuel stories, rumors about acetone were already moving through workshops, depots, and industrial yards across multiple countries. In post-war Japan, mechanics working on heavy transport vehicles and punishing winter conditions were constantly searching for ways to deal with weak combustion, smoke, and hard starts in freezing mountain regions. Stories like these survived not through official manuals or engineering bulletins, but through whispered trade knowledge, passed from one generation of mechanics to the next as part of the larger folklore of survival, improvisation, and machine reliability. Similar claims appeared in Europe, where pre-war and mid-century engineers experimented with fuel behavior, combustion quality, and emissions under harsh operating conditions. From military aviation circles in the 1930s to mining and transport environments in the late 1940s and 1950s, the same pattern kept appearing. When fuel quality, climate, altitude, or load created problems, mechanics searched for any compound that might change ignition behavior, reduce smoke, or improve consistency. In the United States, wartime logistics created the perfect breeding ground for these kinds of stories. Mechanics, engineers, and transport crews were under constant pressure to stretch range, protect engines, and keep supply chains moving in brutal environments where every extra mile mattered. That is exactly how legends are born, not always from polished academic labs, but from desperate field conditions where people try everything, remember what seemed to work, and pass those stories forward long after the original context is gone. The result is a global trail of anecdote, rumor, and partial documentation that gave acetone an almost mythic reputation in certain automotive circles. To believers, the pattern is too widespread to dismiss. To skeptics, that same pattern is exactly what makes the story so powerful. Scattered observations, repeated across decades and countries, can sound like proof even when the evidence remains incomplete, inconsistent, or stripped of context. And that tension is what makes this story so compelling. For decades, mechanics and operators believed they had found a buried chemical shortcut hidden in plain sight. The real question is not just whether they believed it worked, but why that belief became so durable, and what modern science actually says when folklore finally collides with controlled testing. At the heart of this entire debate is a concept most drivers have never heard explained properly: atomization. When fuel enters an engine, it is not supposed to behave like a liquid stream. It is injected as a fine spray, breaking into microscopic droplets that mix with incoming air. The smaller those droplets are, the more surface area they expose, and the more completely they can burn during combustion. In simple terms, engines don't run on liquid fuel, they run on vapor. And the entire efficiency of modern engines depends on how well that liquid fuel transforms into an even, combustible mist at exactly the right moment. Modern gasoline, especially ethanol-blended fuels, is already engineered with extremely precise volatility and atomization characteristics. Fuel injectors operate at high pressure, often thousands of psi, specifically designed to shatter fuel into ultrafine particles before ignition. This means that in a properly functioning modern engine, atomization is not a flaw waiting to be fixed. It is a system that has already been optimized through decades of engineering, emissions regulation, and laboratory testing. When inefficiencies occur, they are usually caused by worn injectors, carbon buildup, poor maintenance, or sensor issues, not a simple chemical deficiency in the fuel itself. This is where the viral surface tension argument enters the conversation. It sounds compelling because it uses real scientific language. Surface tension does influence how liquids behave when they form droplets. And in controlled laboratory conditions, changing a liquid's composition can alter how it spreads or breaks apart. But inside a modern combustion engine, that process is dominated far more by injector pressure, temperature, turbulence, and timing than by small changes in bulk liquid properties. In other words, the engine's mechanical and electronic systems are doing the heavy lifting, not a minor additive changing droplet physics in a meaningful, consistent way across real-world driving conditions. There's also the widely repeated claim that certain solvents can improve combustion by cooling the intake charge due to their heat of vaporization. While evaporative cooling is a real thermodynamic effect, modern engines already account for intake temperature, air density, and fuel-air ratios using sensors and onboard control systems. Any external attempt to manipulate this balance without calibration can actually disrupt the finely tuned combustion process rather than enhance it. That is why automotive engineers design fuels, injectors, and engine maps as a complete system, not as independent variables that can be safely altered in isolation. When it comes to scientific studies, this is where the story becomes more nuanced than viral claims suggest. Some laboratory-scale experiments have explored how small chemical changes affect combustion behavior under tightly controlled conditions. In those environments, researchers may observe variations in efficiency, emissions, or burn characteristics. But translating those results to real-world engines across different vehicles, fuel systems, climates, and driving styles is far more complex. What works under controlled testing does not automatically scale into a universal, safe, or repeatable improvement for everyday drivers. That gap between laboratory observation and real-world application is where most miracle fuel hacks lose their credibility. And that is the real turning point in this story. On one side, you have a concept that sounds scientifically convincing: change the fuel, change the burn, improve efficiency. On the other side, you have decades of automotive engineering, emission standards, and field testing that have already optimized how fuel behaves inside modern engines. The question is not whether chemistry can influence combustion. It absolutely can. The question is whether simple, unregulated modification can outperform systems that have been engineered, tested, and refined at a global scale. That is where belief, science, and reality begin to separate. The final piece of this story is not about a miracle liquid or a hidden dosage formula. It is about understanding how to improve combustion the right way, using methods that are actually validated by automotive engineering and safe for long-term use. Modern engines are designed as tightly controlled systems, where fuel composition, injection timing, pressure, and air intake are all synchronized. When performance drops or fuel efficiency declines, the cause is rarely a missing chemical. It is usually something far more practical: partially clogged injectors, carbon buildup on intake valves, degraded spark plugs, incorrect air-fuel ratios, or even low tire pressure increasing rolling resistance. These are not hidden secrets. They are measurable, fixable factors that directly impact how efficiently your engine converts fuel into motion. If you want to achieve the kind of efficiency gains people chase with fuel hacks, there's a proven pathway that mechanics and engineers actually rely on. Using manufacturer-approved fuel system cleaners, maintaining clean injectors, replacing worn ignition components, and ensuring your sensors are functioning correctly can restore combustion quality in a way that is both safe and repeatable. Even simple actions, like keeping your air filter clean, using the correct engine oil viscosity, and maintaining proper tire inflation, can deliver noticeable improvements in fuel economy over time. These changes may not feel as dramatic as a single, secret liquid, but they are grounded in decades of real-world testing, and are the reason modern engines can achieve such high efficiency compared to older designs. And this is where the financial reality becomes clearer. The idea that a single cheap chemical can replace an entire industry is powerful, but the truth is that long-term savings come from consistency, not shortcuts. Spending a small amount on proper maintenance can prevent much larger costs later, from injector replacements to engine damage. The real hidden system is not a bottle on a shelf. It is the network of engineering decisions that make your engine perform the way it does, and the maintenance habits that either support or degrade that performance over time. So before chasing any shortcut that promises instant results, ask a more important question. Is this improving the system, or is it interfering with it? Because once you understand how combustion actually works, you stop looking for hacks. And you start making decisions that genuinely extend the life of your engine and reduce your fuel costs in a reliable way. And in the next video, we're going even deeper into the world of automotive myths versus reality. There's a viral claim about a kitchen powder that can supposedly extend battery life in seconds, and just like this story, it sounds simple, cheap, and almost too good to question. But once you break it down scientifically, the truth is far more interesting and far more important than the claim itself.